Hello my dear student, today we are in lecture number 61 of new chapter. It is Magnetism and Matter. It is lecture number 61, Magnetism and Matter, chapter 5th of NCERT. This is the code of our chapter, Magnetism and Matter. So my dear students, in last class we have studied about the magnetic dipole, and we have studied all the magnet itself is considered as a magnetic dipole because we cannot obtain any magnet in isolated pole. So all the magnets are already a dipole. All right. When you will break a magnet, it will induce pole in itself. Today we are going to start this lecture with the oscillation of magnet, that is the magnetic dipole, when it is placed in uniform external field. All right. So it is the oscillation of dipole. Oscillation of dipole. You can say nature or the behavior of dipole placed in uniform magnetic field. This is a uniform magnetic field, my dear student. Here this is the uniform magnetic field. Suppose it is B. All right, the magnitude it is B. In a stable, most stable equilibrium, when we'll place the dipole, that is the magnet, in this way, all right, is north and south pole aligned in this direction, it is in most stable equilibrium. But now the question, what will happen if we'll disturb slightly along this axis? If you will displace this dipole slightly from its initial position, it will try to regain its actual position. All right, and it will start moving towards its actual position. Remember, this displacement is very small. From this one, the dipole is being displaced for the very small angle theta. This theta is very small. All right. Since this magnet having some moment of inertia, because it is having mass, so due to moment of inertia, it will regain to its actual position, suppose from here. But while going to the mean position, due to its inertia, it goes little further. And again it regains its position, and it happens for some time, and it looks like oscillating on its actual line. Okay, this line, and this will be considered as the simple harmonic motion. It start performing simple harmonic motion. We are going to find out the time period of that harmonic motion. All right, my dear student. Yes. So initially magnet is in stable state. Okay, initially it is in stable state. As we will apply some force, so we need to apply here the torque, that is the torque applied, okay, this will be equals, who will be balance this torque actually? So this torque that we apply, actually it will be countered by the torque applied by the magnetic force. A magnetic force is acting, you can say here the force is acting in upward direction from this north pole, which always try to move along the magnetic field, and the south pole in this direction. Am I right? Yes. Now this particular force provides the counter torque and it goes to its initial position and try to regain its original position. So thus applied torque will be equal to torque due to rotational inertia. You can say torque due to rotational inertia. And remember, this rotational inertia actually, my dear student, experiencing the torque due to magnetic field over here. We can write here the torque applied, it is the tau, it is m cross b, because against the field we have to apply the force, m cross b. M, it is the magnetic moment, mb sine theta. We can write, my dear students, we are writing here the magnitude only, mb sine theta. And for very small twist, this tau could be written as mb theta. Equation 1. Am I right? Yes. Now this torque will be counterbalanced by the torque due to inertia, and we know that tau is equals to I times alpha. What is this I? I is nothing but the moments of inertia of this bar magnet. Okay, my dear students, here I have been written, I think it is finding, it is written I is equals to moment of inertia. You can write it is the second equation. And remember, this is the counter torque, so it will be in opposite direction. So the minus sign we will use. Here this 2 mb theta will be equals minus I times alpha. Here the alpha is the angular acceleration, you can say. Now here the alpha can be written as mb by I times theta. Yes, could we write? Yes, my dear student. Now here this alpha can be written as a d2 theta over dt square. Okay, here the minus also, the minus mb over I times theta. Now we are going to compare this equation using the standard equation of SHM, and that standard equation of SHM is d2 theta by dt square, it is minus omega square theta. This is the standard equation of SHM. If you will compare this standard equation of SHM with the equation we got here, then this omega square will be equals mb by I. So we will have here the time period. We can write, my dear student, mb over I, it is equals omega square, or the omega is equals to root under mb over I, and which is equals 2 pi by t, or the t can be written as 2 pi root under I by mb. All right, so this is the time period of oscillation that the magnetic dipole performing the SHM on its axis if it is disturbing from its stable state. Okay, my dear student, so this is the SHM. Now we will proceed for the Gauss theorem in magnetism. Okay, let me rub this. Gauss theorem in magnetism. I hope you remember, my dear students, the Gauss theorem that we have studied in electrostatic. Here we are going to apply the Gauss theorem in magnetism. Gauss's theorem in magnetism. Very important, my dear students. It is mentioned in NCERT very carefully. Now, before applying the Gauss's theorem, let me discuss here the field lines of magnet, which is not very difficult. We have studied already. This is the North Pole and South Pole. All right. How the magnetic field arranges around this magnet, it looks like this one. All right. Yes. This magnetic field lines. You can see, my dear students, here the magnetic field lines from North Pole, it is moving out, emerging out, and it is moving in to the magnetic field. Now, to apply the Gauss law, we know that we need to confine a Gaussian surface. Now, you can take the Gaussian surface, the two Gaussian surface, okay, one by one. Here, one Gaussian surface will be enclosed, will enclose the one end, okay, or you can take, for your simplicity, for your satisfaction, the entire magnet inside the Gaussian surface. This is the Gaussian surface 1 and this is the Gaussian surface 2. One by one we will study. This theorem is equally applicable for both, and this is perfect theorem to explain the field lines, confining of magnetic field lines. According to this theorem, my student, according to this theorem, the total magnetic flux, okay, actually this Gauss theorem is completely related with flux, that is the magnetic flux, and we know that the magnet always exists in dipole nature. We cannot have monopole, but here we will apply this Gaussian surface 1 for the monopole also, and we'll find that this Gauss theorem is applicable. All right, so the actually statement of the Gauss theorem, you can write, my dear students, I'm telling you, the surface integral, okay, the surface integral, if we are taking here the surface, this one Gaussian surface, then we can have elemental surface. It is the surface integral of magnetic field, surface integral of magnetic field over a closed surface must be equals to 0. It was in electrostatic Q by epsilon naught, but here it is 0. What does it mean? It means the surface integral of magnetic field will not encloses or will not count any flux. The total flux will be 0. All right. This is the magnetic. This is the Gauss theorem in magnetism. All right. So we can write here the theorem in a mathematical way. B dot ds must be equals to 0. After writing the statement, you can write this mathematical equation for the Gauss theorem. B dot ds, it is 0. Okay, my dear students, in another word, you can say in another word that the total magnetic flux through any closed surface, total magnetic flux phi net through any closed surface must be equals to 0. You can say this must be equals to 0. All right. If you're looking this Gaussian surface 1, my dear students, you can see here the total field lines it is entering and exit to this Gaussian surface are same. That's why the flux will be 0. The counting of field lines will be 0. And if you are taking this entire, so you can see the total field lines leaving this North Pole is not moving out from the Gaussian surface, and if it is moving out, then exactly it enter to the Gaussian surface. It means there is no net counting of magnetic field lines out or in, that is the net flux is 0. And this is the Gauss theorem. All right. Now, one question we should solve here using this theorem, if we understand it very well. This question have been asked in a very famous examination of engineering, my dear students. Here the question for you: which of the field pattern gives given below, I'm giving here, let me give you the options. These are the pattern. All right, let the fill out. Okay, the option A, option B here. The filled in. All right, the option B, one more. The pointing here, the dot. All right, here the direction I'm representing, option C, and the last one, it is the option D. Now, option D. Now the question, it was, among this four field pattern, which of the field pattern is valid for both electric as well as magnetic field? This was the question. Which one is valid for both electric as well as magnetic field? Which one is representing here? This is your question, my dear students. So let me discuss one by one here. The first one, A. Suppose if this pointing represent the direction of current, that will give you the direction of electric field as well. If this is the direction of current, then dot represent outward. All right, it is representing outward, and we know that if this will be the direction of current, this cannot be the direction of magnetic field. If it is charge, positive charge, then probably this one is representing the direction of electric field, no doubt. But this one is not representing electric as well as magnetic field, so this is not the right choice. Now the next one. Here again, the point representing the negative charge but not the electric and magnetic field both as well. Here, suppose if this dot point, this dot point is representing the direction of current in upward direction, of course, then the circle represents the magnetic field. Exactly. So this one is representing electric as well as magnetic field. But if this circle representing the electric field, that is the direction of current, then of course this pattern will be the direction of magnetic field. We know very well. Okay. So this is representing electric as well as magnetic field. Okay, now come to the option D. Whether this is representing the electric and magnetic field as well. So the answer is no. This is not representing electric and magnetic field. If you will take any of the loop as the electric field, that it will be wrong. And if you take any of the loop as magnetic field, then it is correct. But where is the electric field? You cannot have any choices of electric field over here if you take in this circle as the magnetic field. So those three options, A, B and D, are not representing electric as well as magnetic field, but this D is representing electric and magnetic field both. Now in the next topic, we'll move to the cutting of magnets. Okay, cutting of magnets. Here in this topic, we are going to study, if we'll cut a magnet, then how the magnetic moment will affect. Okay, my dear student. So in two ways we will cut a magnet. Okay, in two ways we will cut a magnet. One, if we cutting this magnet perpendicular to the length. Okay, then suppose we are having a magnet, this one of pole strength m and dipole length it is 2L. What will be the magnetic dipole moment, my dear students? We can write here the magnetic dipole moment as m into 2L. Let me make this as equation 1. Now we are going to cut in lengthwise. This was a magnet and we cut in 2 pieces. The one thing you should remember, my dear students, when you will cut the magnet in this way lengthwise, okay, lengthwise, then there will be no change in pole strength. If m is the pole strength, then it remain constant. Okay, in this way the pole strength remain constant. Now, but what will change? The length will change. Okay, if you cut in 2 equal halves, then this length will be L and this will be the length L. Now m dash, suppose the dipole moment, if it is changed m dash, then we can write the pole strength into length of the dipole and it is L. So you can see the pole strength, dipole moment has been changed. How much it is? So the m can be written as 2 times m dash. It means m dash it is m by 2. Alright, now the second one. Okay, here you can see as you cut the magnet to decrease its length, the dipole moment increase by 2 times. Decreasing the length, dipole moment increase. Now the next. If we'll change the cross-sectional area of the magnet and cut parallel to the cutting parallel to the length, okay, then what will happen? Here what will happen, my dear students? The cross section will change, but the length of 2 pieces will not change. And remember one thing, pole strength will also reduce by half. If you will cut in this way, so the pole strength will reduce by half. Why? Because at the end of the magnet, since the cross-sectional area is being changed, and due to the cross-sectional area being changed, the pole here having the number of loops of current, it will be also changed. That's why we can say here the pole strength will be decreased and it will be halved. Okay. Now here m dash it is equals to pole strength, it is m by 2 into length. How much? Length remains same. Oh, it was 2L, I think. Length remains same. It is 2L. So the m into L, it is m dash. Okay. Again, you can see here the m dash is ml. Here also m dash equals ml. It means m dash it will be m by 2. So what is the basic point we got, my dear students? We got that either you are changing the length of the magnet or you are changing the cross-sectional area of the magnet. Magnetic dipole moment in both the case remain same, changes with the same amount, and it is half the actual one. Okay, my dear students. So this is the particular topic from cutting of the magnet. Okay. Now, my dear students, let me discuss few simple question, and you have to solve this question at your home. This is your home assignment, because I have not given much question in my assignment from this chapter. That's why I'm giving you in the class. Okay. So the very simple question, 2 or 3 questions for your practice, not more than that. The first question, my dear student. I hope you can write the data quickly, or you can write the question as well. I'm just dictating. It is a short bar magnet has a magnetic moment if this is a short bar magnet, okay, short bar magnet having the magnetic moment of 0.24, it is 0.24, okay, joule per Tesla. This is the magnetic moment it is given. Okay, you have to calculate the magnitude of the magnetic field produced by, you have to find B. All right, magnitude of magnetic field produced by the magnet at a distance of 10 centimeter. How much? At 10 centimeter from the center of the magnet on the axis of its magnet. From the center you have to find at this distance the magnetic field. Okay, again I'm telling you, a short bar magnet, this short bar magnet has a magnetic moment of this much, 0.24. Calculate the magnitude of the magnetic field, okay, at the point which is 10 centimeter from the center of the magnet. Okay, my dear students. Now the next question. Again, a magnet is 0 point, the length of magnet I'm giving you. Suppose the magnet of length 0.1 meter, 10 meter long, and its pole strength is 12 ampere meter. Okay, the pole strength it is given, m equals to 12. All right, it is given. Find the magnitude of the magnetic field. You have to find again the B. Find magnitude of magnetic field at a point on its axis at a distance 0.2 meter from it. Again I'm telling you the question. A magnet is 0.10 meter long and its pole strength is 12 ampere meter. Find the magnitude of the magnetic field B, that is magnetic field B, at a point on its axis at a distance of 0.2 meter from it. Okay, from it you have to find, from one end on its axis you have to find the magnetic field. All right, third question, my dear students. The third question, it is suppose the third question. Okay, let me do this question. What is the magnitude of the equatorial and axial field due to a bar magnet of length 5 centimeter? 5 centimeter, magnet length at 5 centimeter at a distance of 50 centimeter from its midpoint. Okay, the x it is 50 centimeter. If you are taking axial point, then 50 centimeter from axis, from center. If you are taking equatorial point, then 50 centimeter this one, otherwise 50 centimeter is this one. You have to find magnetic field here and here. Again I'm telling you, what is the magnitude of the equatorial and axial field due to this bar magnet? Okay, due to this bar magnet of length, it is given 5 centimeter. Okay, at a distance 50 centimeter from its midpoint. The magnetic moment of the bar magnet is given 0.40. Okay, magnetic moment is given, it is given 0.40. All right, so those three questions. Okay, my dear student, these are the topics that we have covered from the beginning of this magnet. From next day we will start the earth magnetism. Okay, my dear student, so this is all about the today's lecture. Thank you very much.